This is section 6.3, Confidence Intervals for Population Proportions. In this section, we'll learn how to find a point estimate for the population proportion, how to construct and interpret confidence intervals for a population proportion, and how to determine the minimum sample size required when estimating a population proportion. The population proportion P is the probability of success in a single trial of a binomial experiment. The point estimate for P, the population proportion of successes, is given by the proportion of successes in a sample and is denoted by P hat equal to X divided by N, where X is the number of successes in the sample and N is the sample size. The point estimate for the population proportion of failures is Q hat, which equals 1 minus P hat. The symbols P hat and Q hat are read as P hat and Q hat. Let's look at an example for point estimate. In a survey of 1,550 U.S. adults, 1,054 said that they use the social media website Facebook. Find a point estimate for the population proportion of U.S. adults who use Facebook. Let's look at the solution. The number of successes is the number of adults who use Facebook, so X equals 1,054. The sample size is N equals 1,550. So the sample proportion is P hat equals X divided by N, where X is 1,054 and N is 1,550. In this example, P hat equals 0.68, and if we multiply that by 100, we'll end up with 68%. This means 68% of the 1,550 U.S. adults said that they use the social media website Facebook. Now let's talk about confidence intervals for a population proportion. Constructing a confidence interval for a population proportion P is similar to constructing a confidence interval for a population mean. You start with a point estimate and calculate a margin of error. In this case, our point estimate is P hat, and we add and subtract the margin of error E, where E is the critical z-score multiplied by the square root of P hat times Q hat divided by N. The probability that the confidence interval contains the population proportion P is confidence level C, assuming that the estimation process is repeated a large number of times. To construct a confidence interval for a population proportion, we're going to go through the following steps. First, we're going to identify the sample statistics N and X, our sample size and our number of successes. Second, we find the point estimate P hat using those sample statistics we found in step 1. Step 3 is to verify that the sampling distribution of P hat can be approximated by the normal distribution. Notice that for population proportions, confidence intervals for population proportion, we use N times P hat, which must be greater than or equal to 5, and N times Q hat, which must be greater than or equal to 5, in order to verify that the sampling distribution can be approximated by the normal distribution. Step 4, if we need to, we'll find the critical value Z sub C by using the inverse norm function on our calculator. Step 5, we'll find the margin of error using the formula, and we'll use that margin of error in step 6 to find the left and right endpoints and form the confidence interval. Step 7 is to interpret the results of that confidence interval. Let's look at an example. We want to use the data in example 1 to construct a 95% confidence interval for the population proportion of U.S. adults who use Facebook. Remember from our previous example that we already found our P hat value, or a point estimate, which is equal to 0.68. Our next step is to use that point estimate to calculate our Q hat value, or the population proportion of failures. So Q hat equals 1 minus P hat, which is 1 minus 0.68, and gives us 0.32. Using the P hat and Q hat values, we can verify that the sampling distribution of P hat can be approximated by a normal distribution. In this case, we found n times p hat is equal to 1054, which is greater than 5, and n times q hat equals 496, which is greater than 5. Since they're both greater than 5, we can verify that the sampling distribution of p hat can be approximated by a normal distribution. Using our critical z-value of 1.96, which we get by using the inverse norm function on our calculator, we can use that to find the margin of error by substituting in the values for the critical z-score, p hat, q hat, and n to end up with a margin of error equal to approximately 0.023. Using that margin of error, we can now find the left and right endpoints and form the 95% confidence interval. Our left endpoint is p hat minus our margin of error, which is approximately 0.68 minus the margin of error of 0.023, and gives us a left endpoint of 0.657. The right endpoint is p hat plus the margin of error, and that gives us a right endpoint of 0.703. So our confidence interval, our population proportion, falls between 0.657 and 0.703. Another option is to use the TI-83 or TI-84 calculator in order to find the confidence interval. In that case, we're going to use our calculator. We're going to press stat, then test, then arrow down to A 1-prop z int. You're going to input 1054 as the x value, and for n sample size, you're going to input 1550. The confidence level is 95%. You convert that to a decimal and input 0.95. Arrow down to calculate and press enter. And you'll see in parentheses 0.657, 0.703. This is the confidence interval. It's the same thing we found in the previous slide using the calculations. On this slide, you can see the number line, and you can see in the center is a 0.68, which is our population proportion estimate, p hat. And then in parentheses, you can see the endpoints of the interval. The final step is to write the interpret your confidence interval, and you do that by writing a sentence. In this case, with 95% confidence, you can say that the population proportion of US adults who use Facebook is between 65.7% and 70.3%. Let's look at another example. In a survey of 674 US males aged 18 to 64, 396 say that they have gone to the dentist in the past year. Construct 90% and 95% confidence intervals for the population proportion of 18 to 64-year-olds who have gone to the dentist in the past year. Interpret the results and then compare the widths of the confidence intervals. The sample size is n equals 674, and the number of successes, x, is 396. P hat equals x divided by n. So in this case, our p hat value is x, which is 396, divided by 674, our value for n. So our p hat is approximately 0.59. The point estimate for failures, q hat, is 1 minus p hat, which in this case is 1 minus 0.59, so that equals 0.41. Using n equals 674, we can verify that the sampling distribution of p hat can be approximated by a normal distribution by multiplying n times p hat and n times q hat. In this case, both of those values, 398 and 276, are greater than 5, so we have verified that the sampling distribution of p hat can be approximated by a normal distribution. The next step is to calculate our confidence intervals. I'm going to use my calculator, and I'm going to go to stat and then test, and I'm going to arrow down to A, one prop z int, and press enter. For my values, I'm going to enter 396 for X, 674 for N, and then I'm going to arrow down to my confidence level. In this case, I'm starting with confidence level of 90. I'm going to arrow down to calculate and press enter. Estimating, I get a confidence interval of 0.556 to 0.619. So I'm just rounding to the third decimal place here. This is the 90% confidence interval. I'm going to do the same thing in order to find the 95% confidence interval. I'm going to arrow down to A and input 396 as X, 674 as N, and arrow down to my confidence level, and I'm going to input 0.95 for 95% and press calculate, and you'll see rounding to 3 decimal places, my confidence interval is 0.550 to 0.625. So interpreting my results, with 90% confidence, you can say that the population proportion of U.S. males aged 18 to 64 who say they have gone to the dentist in the past year is between 55.6% and 61.9%. With 95% confidence, you can say that it is between 55% and 62.5%. So we can see that the 95% confidence interval is slightly wider. Let's look at another example. The figure below is from a survey of 800 U.S. adults aged 18 to 29. Construct a 99% confidence interval for the population proportion of 18 to 29-year-olds who get their news on television. Looking down at the graph, we can see that looking at television, we can see that 27% of 18 to 29-year-olds get their news from television. We're going to use that value as our p hat value. Okay, so from the figure, p hat equals 0.27. So q hat equals 1 minus 0.27 equals 0.73. Using n equals 800, we can multiply 800 times 0.27 and 800 by 0.73 to get values that are greater than 5 to verify that the sampling distribution of p hat is approximately normal. Our next step is to calculate our confidence interval, and we'd like to use our calculator. But notice we are given p hat equals 0.27 in the problem. But in order to enter the information into my calculator, I need the value for x. So if I go stat and then over to test and then arrow down to 1 prop z int and press enter, notice the first thing I need to enter is x, but I don't have an x value. All I have is my p hat. So the first thing we need to do is solve for x. So we know p hat equals x divided by n, and if I multiply n times p hat, I'll end up with x. So p hat times n equals x, so x equals p hat, which is 0.27, times n, which is 800, which gives me 216 for my value of x. So I'm going to enter that into my calculator. My value of n is 800, so I'm going to arrow down to n and input 800. The confidence level I'm looking for is 99%, so I'm going to enter 0.99 and arrow down to calculate. You'll see we get 0.22957 and 0.31043 as the confidence interval. Rounding those values to 3 digits, we get 0.230 to 0.310 as our interval. So with 99% confidence, you can say that the population proportion of 18 to 29-year-olds who get their news on television is between 23% and 31%. One way to increase the precision of a confidence interval without decreasing the level of confidence is to increase the sample size. We can use the formula provided in order to find the minimum sample size needed to estimate P given a confidence level and margin of error E. That's it for now.